All right, today we're doing inclined planes. All right, here's the deal. When you're on an inclined plane, we're going to give this inclined plane just some random angle. And we put a mass on this inclined plane. Now, if I tilted up one of those frictionless aluminum things and I put the cart on it, what's the cart going to do? It's going to slide down. So it's not just going to move straight down. It's going to accelerate straight down. Not straight down, but it's going to accelerate down the inclined plane, right? So if there is an acceleration, what does that mean about forces? There has to be an unbalanced force. There's got to be some kind of unbalanced force which is pulling it down the inclined plane. If we have an acceleration, we have to have an unbalanced force. So let's take a look at the free body diagram of this object on the plane and try to figure out what force that is that's making it accelerate. You got gravity straight down. Now, first common mistake is that people think that because it's on an inclined plane, that gravity is somehow tilted. That's not true. Think about the extreme example. If you put something on a vertical inclined plane, which is a wall, and you drop it, does gravity pull it into the wall? Negatory. Gravity pulls it straight down. So why would it be any different if we had just a small incline? It's not. Gravity acts vertically towards the center of the Earth at all times. Doesn't matter what the motion is, gravity acts straight down. So mg is going to be straight down on this thing. What other forces? What other things are touching it? Plane. And what type of force does a plane exert? A normal force. And by definition, a normal force is perpendicular to the surface that it's on. So the normal force is perpendicular in that direction. I drew that a little bit long. It's okay. Now in this case, does the normal force equal to the gravitational force mg? No. Some angle thing of mg. It doesn't equal mg because if they balanced out, there wouldn't be any acceleration. Plus it can't balance out. It's not the same angle. These two forces can't potentially balance themselves out. So if we were to add these two forces together, what we'd end up with is a resultant force that's down the plane. That resultant force, this thing, whatever it is the cause of the acceleration down the plane. So our objective is to figure out what that unbalanced force is. Now, as it turns out, that unbalanced force is a component of gravitational force. Let's take a step back and talk about what we did in the case of this force. What's the first thing that we did when we had a force at an angle? Or what's the first thing that you did when you had a velocity at an angle?
We did upward, y, x.
Right, we had two different components. There's a part of this velocity which is making it go up, and there's a part of this velocity which makes it go to the right. We called those Vx and Vy. They were not equivalent to this because they're just pieces of it. They're ratios of that part. With forces, we do the same thing. This force can be broken down into how much force is pulling it in the x direction and how much force is pulling it in the y direction. Now we did that because on our axes, this force is at a weirdo angle. So I need to find out how much of that force is pulling in the x and how much of that force is pulling in the y, and then I can deal with it. I can write F equals ma and things like that. Same thing here. F and x and F and y, or sorry, V and x and V and y were at angles, so I broke them down into pieces. So I can tell you how much is this thing moving to the right in the x direction, how much this thing is moving up and down in the y direction. I'm going to attempt to do the same thing here. Now if I have a coordinate plane, it looks like mg is in that plane. The problem is this acceleration is not in that plane. It's at some weirdo angle to that plane, and now I don't know what I'm doing. I want to be able to use kinematics equations. I want to be able to put acceleration in one of those formulas, Vf, Vo, and At, and figure out final velocities and things like that. But I can't do it if acceleration is at an angle. So I do a little mathematical trick. I just pretend like the Earth isn't vertical anymore. I pretend like the Earth is tilted at the same angle that this thing is. So what I can do is I can just rotate my axes. Why not, right? Who wouldn't? That's right. It makes perfect sense, right? Now, what I'm able to do here, and I'll look at these things. Normal force is now in the y direction. If I had friction on it, that would be in the x direction. And most importantly, my acceleration. My acceleration is now in the x direction. So all of my things line up with my new coordinate system, my new axes, except for mg. Just like you broke down these when these forces and velocities were outside of the axes, we're going to do the same thing with mg. When mg is not in the axes, we break it down into its pieces. Now, by some geometry, this angle that's the plane is the same as this angle right there. Can you solve for the sides of that triangle now? The angle's here, and that's the hypotenuse of the triangle. So this is another little right triangle. Yeah, assuming we knew the angle, assuming we knew the mass. I mean, what did we do? We did F cosine theta because it's the adjacent side. And this was going to be F sine theta because it was the opposite side. So what are these? What is this side?
It's the adjacent side.
It's the adjacent side, so sine or cosine? Cosine. So the hypotenuse times the cosine of the angle. mg times the cosine of the angle. And what's the red side here? mg times the sine of the angle. And those are the pieces of mg. This mg sine of theta is the thing that's causing that acceleration. Friction would be reducing that acceleration. What's causing the normal force? mg cosine theta. We looked at the graph of this yesterday, right? What happens to the normal force? Sine theta goes on sine theta is, the mg sine theta is what's responsible for accelerating it down the plane. Yes? Anybody? Are normal force and mg cosine theta equal?
Yes.
How do you know?
It's
Not accelerating, that's better. It's not accelerating in this direction. It's not taking off. And if it's not accelerating, that means the forces have to be equivalent to each other. So in this case, normal force is equal to mg cos theta. If I had a... Sorry? mg cosine theta. Normal force equals mg cosine theta. Yeah. We can, if we showed in the y direction, the acceleration is 0. So we have the sum of the forces in the y equals to 0. Normal force minus mg cos theta equals 0. So normal force is equal to mg cos theta. And we looked at this graph, what happens to the normal force as the angle increases. In this case, the normal force is, normal force mg. Normal force is very, very big, right? On a flat surface, normal force is big. In fact, on a flat surface, it would have a value of mg. And as cosine increased, as this angle changes, the direction of the normal force, not the same with gravity. Definitely want to separate those two things. Huh? Normal force changes its direction. Gravity always acts straight down. So normal force is decreasing. Normal force is decreasing until what happens in this case? Normal force is 0 and falls off the wall. So normal force is going to decrease. Is it linear? It looks linear because I drew a line. Is cosine and theta linear?
No.
And what's cosine theta look like? What's cosine look like?
Curvy.
There you go.
Yeah, right? I had it right the first time. That's not it though, because we're not looking at how it looks underneath the axes.
Who cares about that?
Cosine theta looks like that, right? We're only looking at this little chunk.
So pi over 2 is 0. What's cosine pi?
1. So we're looking at from 0 to 90. So we're looking from 0 to pi half.
Pi over 2 is
0.
0.
Cosine of 0 is 1. Cosine of pi over 2 is 1 or 0. So we're just looking at the first quarter of a period. Anyway, the important thing to note here is that normal force is going to decrease as we increase that angle. Now, if normal force decreases, so normal force is equal to mg cos theta. Cosine theta is going to get, as this number, as theta gets bigger, that number is going to get smaller until normal force is equal to 0. Okay. Everybody got it? More or less? Mostly less. All right, let's look at. Here, where are we going? Number 1. Curved slope would cause varying acceleration, and we'd probably have to use energy to solve that.
Did you have graphs?
These graphs?
No.
This graph? It looks like a cosine graph. So normal force equals mg cos theta. Mg is a constant, so it doesn't matter that that's there or not. So if we graphed y versus x, and theta was x, it would look like a cosine function. So let's look at the situation where there's absolutely no friction. we got these tracks that we can put something on and say no friction. They have a little bit. We're just gonna pretend like we don't have any friction. It doesn't really happen in real life, no. But ice is still got friction.
Ice on ice.
Does Jesus have friction?
Well, no, it's just like this.
I guess. All right. So what force did we say is accelerating it down the plane?
MG.
More specifically, mg
Cos
sine theta. mg cos is going against normal force, so mg sine of theta is the force that's acting on this. So mg sine of theta is the resultant force that acts down the plane. And if there's no friction, are there any other forces in the x direction? Now keep in mind, our x direction is this way.
No, there are not.
There are no other forces in the x direction. So when we sum forces in the x direction, the only force we have is mg sine of theta. And what conveniently happens to the mass in this equation? Divides out with the other m. So the acceleration is equal to g times the sine of theta. It's independent of mass. Now we talked about this way long ago when we talked about gravity. Gravity acts on everything equally, right? So if I were to drop this nail and this nail, they have different masses. One is a gigantic nail and one is a tiny nail. If I drop these two things, gravity acts equally on both of them. They hit the ground at the same time.
Well, I think
They did. Yeah. Gravity acts on everything equally, so it makes sense that this is independent of mass. Acceleration on a plane is g sine theta, if it's frictionless. What if I'm just dropping things straight down? What's the angle of the incline?
90 degrees.
90 degrees. What's the sine of 90?
1.
1. So the acceleration is equal to g. So if we just had a vertical surface, that's a 90-degree angle. Sine of 90 is 1, so the acceleration is equal to gravity, which is what we expect. Again, independent of mass. That's a g. G.
That actually kind of cool.